Let me introduce you first. Our next speaker is Nina Balcan from CMU. I guess where Avram spent, I don't know how many years and how many visits I went there to visit it. Then she's going to talk about the learnability of complex objects.
Yeah, thank you, Ishai. Cool. So let's see. So I guess I'll start by obviously saying happy birthday, Avram. And actually, over the lunch, I thought about, first of all, I agree with everything that Santosh and Adam and John, everybody that talked before me said about you. And I was trying to think whether there is something I can say that I didn't say. And I guess there is one thing that I think it wasn't said yet. So not only Avram was an amazing PhD advisor, but I think we also had amazing students and friends, collaborators that over the years they become my collaborators and friends too. So it's in addition to him being an amazing advisor, I think also like an amazing community. I think it was awesome. So I guess he competes with Manuel on now on that. So okay, cool. But of course I agree with everything else that was said as well. All right, so, and by the way, my initial title was broader, but I realized I only have 35 minutes, so I'll scale down a little bit what I'm talking about, and I kept work that is joined with Avram. Cool, so it's about learning complex objects in modern AI. Of course, you know, we've heard AI is everywhere, and also AI is currently used to learn much more complex tasks than people were able to learn even a year ago, right? So, you know, it has been used to solve, I guess, non-trivial math problems like International Math Olympiad questions written in plain text. It was just used to solve one of Erdős's problems. Also, people are using all the time AI to come up with algorithms for solving problems that appear hard in classic theory of computing models. AI is used by agents for planning events. And recently, there has been even hope that these AI systems will be able to propose and carry out innovative research agendas on their own, right? So really big goals. So it's used. So AI is used for much more complex tasks, and also now it's obviously used in much more high-stake domains as well, like banking, medical domains, also diplomacy and international relations. And moreover, often now we have agents learning in the presence of other agents. So a much more, I guess, much more complex systems to analyze than what I guess we were analyzing, say, 3 years ago. And actually, in order to think about these modern AI systems, I think we need to build on and extend on ideas from many different fields, not only machine learning theory and theory of computing, but also game theory, algorithms, optimizations. And this multifaceted approach is, I think, very important to analyze and design better AI. And actually, Avram, I was so lucky I was his advisee, because actually he has expertise not only in machine learning theory, but in all of these other areas. So now they become very helpful to analyze modern AI. Okay, but again, my title was a little bit broader, so because I only have less time. So rather than talking about various aspects of learning, of learnability in modern AI, so I'm going to focus on learnability of complex objects. And the first part of my talk, and most of my talk, will be on learning verifiers for chain-of-thought reasoning that can help flag off-track inference and might mitigate catastrophic failures of LLMs, like appearing convincing by being wrong. And more generally, they could potentially enhance some sort of, I guess, generation capabilities of these LLM generators. So this will be most of my talk. And this is joint work with, with Avram, Jiwan Lee, my former student Ravi Sharma, who is now a postdoc at TTIC, and also more recent work also of the same set of authors, but also of my student Corina, who is here in the room. So this will be most of my talk, but also towards the end, I also want to tell you, because it also relates to learnability of complex objects in modern AI, I also want to tell you a little bit about learning algorithms for solving problems that remain hard in classic frameworks. This is something that I've been doing in my group in the past 10 years extensively. And here I'm just going to spend a couple of minutes, maybe 5 minutes, actually, this will be a brief preview of Avram's talk, because I think Avram will talk about more about that on Thursday. So I'm talking about the first part of my talk is joint work with Avram. The second one is just a brief preview of his talk. or introduction. I mean, not preview, but introduction. Background. Think about it as background. Cool. All right, so now I'm going to talking about learning verifiers. Again, it's based on these two works. And here's the motivation. So again, we've heard a lot these days that LLMs with channel for reasoning are used for solving very interesting questions these days, like mathematical questions. Agents use them for planning events. But as we've also heard, these LLMs sometimes make mistakes. And the key point is that learned verifiers for natural language reasoning might help us correct mistakes. And in fact, turns out that actually these verifiers are already used by frontier models. So for example, in the context of math, DeepSeek Math V2 they highlight having verifiers as a key component of their system. Or as another example, there is this system, Alethea, released by, I guess, DeepMind. So it's powered by Gemini DeepThink. And if you look at their architecture, so they don't tell us a lot of details, but if you look at their architecture, schematic architecture, in addition to the generator component, the LLM, they also have a very explicit verifier component. Okay, so already frontier models incorporate verifiers. That's one motivation. It can help us, so these verifiers can help us correct mistakes of frontier models. Now, if you are a professor at CMU, and some of my colleagues believe that these LLMs will be so great soon, they'll never make mistakes. And so even if you believe that these LLMs will be so amazing, if you're going to use them in critical domains, like very high-stake domains, high-stakes domains, then you might still want to use verifiers to increase your confidence to use them. So even if the LLMs become amazing, if you have these verifiers, it can increase your confidence to use them in critical domains, like medical diagnosis, for example. And finally, another piece of motivation, actually, many people here submit papers to all these major conferences, from theory of computing to algorithmic game theory to machine learning. And all of these conferences now have a pre-submission verification service. So if your paper is ready a few days before the deadline, you can submit to a verification service that they offer to you, and they point to some potential mistakes so that you can update your paper. Now, of course, their services are not particularly, they have not been particularly accurate so far. They point to things that are no mistakes and so on, but it shows that there is a lot of interest. So if you could have verifiers, it could also be helpful in this context. All right, so that's the motivation. Now, in this work, in this NeurIPS 25 paper, we had the first work on learning verifiers for chain of reasoning. I guess the first work on providing theoretical guarantees for learning verifiers for chain of reasoning in natural language. Okay. And now I'm going to try to describe to you the formalism, right? The mathematical phrasing of the question. So here is the goal. So we are trying to train a verifier for the following task. So we have as input a problem statement and a sequence of reasoning steps. Okay. So for example, and then the goal is to output yes, the sequence of reasoning steps is correct, or the sequence, or if not, we need to point out to the location of the first mistake. Okay, that's the task. So here's a quick example. So my problem statement might be, please give me a step-by-step instruction to book my trip, for booking my trip to NeurIPS, a major machine learning conference. So this is a problem statement, and maybe these are our steps produced by the LLM. Step 1, register before the deadline. Step 2, adjust your calendars to block December 6th to December 12th. That's correct. This is when NeurIPS happens this year. Step 3, book a round trip United to Sydney from December 5th to December 12th. It's again also good because NeurIPS will be in Sydney. But step 4 says book a hotel in Pittsburgh from December 6th to December 12th. And so here we should flag as being a mistake because if the conference is in Sydney, we shouldn't be booking a hotel in Pittsburgh. Right? So that's basically the problem. So we are given as input we are giving as input a problem statement and the sequence of reasoning steps, and we either have to say yes, the set of reasoning steps is correct, or otherwise point to the location of the first mistake.
Is the steps, like in your example, the steps are independent?
They could be dependent.
Right, so it could be that you got the wrong order of the correct steps.
Yes, so let's see. Okay, how do you formalize this as a learning question? So because you are getting to a deeper question. What's the learning question? So to formalize as a learning question, I need the machine learning terms to come up with some inductive bias, right? So I need to assume something about the problem I'm trying to learn, right? And what's my inductive bias? right? Because otherwise, if I don't have an inductive bias, I can prove lower bounds. So what's the inductive bias that we use in this work? It's a very specific form of inductive bias. So we assume that each proof can be easily verified step by step. Okay? And so what do we mean by this? Now, of course, in typical machine learning terms, I'm not going to assume that I have a verifier in my hand. I don't necessarily know the verifier, but I'm assuming that there is some family of hypotheses, some hypothesis class, and these functions that I'm going to call them verifiers, they take as input a problem statement and a reasoning trace or a prefix of a reasoning trace, and they output whether the last step is correct or not. Okay, so I'm assuming that there is this family of verifiers, the hypothesis class, and then I'm going to assume that there is a target function in the class. I'm going to call it H star, that agrees with how the human oracle will label the reasoning trace, or label how the human will label. We agree with the label given by a human on any problem instance and any prefix of a reasoning trace. Okay, so that's my inductive bias. I'm assuming that the proof can be verified easily step by step, and in particular, there is this family of functions, the hypothesis class, and then there is a target function in the class, this class of verifiers that agrees with how the humans would verify each step.
Question.
Yes.
So in previous example, steps 2 and 3 could be swapped.
They could be swapped, yeah. And if the human, but if the human would agree with that, we'll be fine. So I'm just going to try to emulate how you would answer. So actually, let me.
So there exists an H star, basically.
Exactly, there exists an H star. Okay, perfect. But they're perfect questions. So let me give you an example, actually, because I have a couple of examples here. We can go back to the. So, for example, like if I'm thinking about verifying proofs, right? So H star could encode the way I would personally verify proofs, and in fact, I could have a different target function if I'm verifying learning theory proofs versus when I'm verifying game theory proofs. I could have a different target function, right? And moreover, in fact, I could even have a different target function when I verify proofs of my undergraduate students in the class versus proofs of my graduate students. Because I might give a lot more strength to the undergraduate students, and I'll be very picky with my graduate students. They know some of them are here in the room. Cool. Right? So this, in the context of proof verification, H star encodes how they verify could encode how would I verify each step of a proof myself. Like in the planning example, like going back to the question, this could just be, H star would correspond how would I basically label a plan myself, right? And they could, yeah, there has just to be some H star in the class, right? There could be multiple H star that are consistent, but one of them suffices. And I guess what's interesting that H star actually in the context of planning, it's interesting because, I might have a different H star from Lenore because, for example, I might prefer to fly with United Airlines and Lenore might not like United Airlines. So it's also, again, the target function might depend on the user. Okay, so that's our inductive bias. But each proof can be easily verified step by step. So, and if that's our inductive bias, then a natural approach to learning is to then, to learn a verifier of this form, right? So just learn a verifier that can take in any problem statement and any prefix of a reasoning trace and tell us yes or no, is the last step of the reasoning trace correct or not? And then if we are giving a new instance, what we're going to do, we're going to run it on all prefixes. So if we're giving an input, an instance, which is a problem statement and a reasoning trace, we're going to just run it on all prefixes of the trace to determine the label. So for example, here, this is my input and this is my reasoning trace. I'm just going to run it on prefix of length 1, I get yes. I move it to the prefix of length 2, I get yes again. So this is tau 2 is correct given beta 1. And then I run it on the prefix of length 3, and then here, if I get no, then I stop and I say I have mistake at step 3. This is how I apply the hypothesis that I learned, the verifier that I learned. Or for example, for the input on the right, if this is my input, the problem statement and the reasoning trace, I apply it on all prefixes of all length, and if I get yes everywhere, I just say yes, the whole sequence is correct. The whole reasoning trace is good. I found no mistake. Okay?
Sorry.
Yes?
So the error doesn't depend on, for example, if there's a mistake in the last step versus mistake in the first step, in both cases count it as like error.
In this formulation right now, but there could be in this formulation right now, but there could be this what we've done so far. But there's a very interesting variations where you might do something that's. And in fact, we've been talking with Corina and some in the current work. We just want to flag the first mistake, and and actually the error depends. Are you flagging correctly the place of the first mistake, or not? That's what the error depends on. Okay. Yep.
In this variation, you're also reading the proof in some forward order, right?
Yes. Yes. It could be some other. Yeah. This is what we do so far. Yeah. That could be many potential. interesting extensions.
So,
Yeah.
so I'm slightly confused. How is it different in sort of the regular realizable learning?
Yeah, that's exactly what I'm going to talk about.
Okay.
Perfect. Stay tuned. Okay, good. So, all right. So, okay. So that's the problem. And given that we assume that this inductive bias, there is a verifier. I have a hypothesis class of verifiers, and there is a perfect verifier in my class. Well, I want to learn a verifier that is able to accurately verify new traces. That's the goal. And the question is, how do I do it? But also, you might ask, why do I want to do it? Okay, so I guess motivated at the beginning, but let me tell you a little bit more precisely one concrete use case that we actually analyze in our most recent work, which is once we have a trained verifier, we want to improve the accuracy and the efficiency of a pre-trained LLM generator or agent. So imagine a situation where you have a pre-trained LLM, it's frozen, I cannot modify its weights, but it's great, but not perfect, and I want to potentially improve it. So what I'm going to do, at the training time, I'm going to train a verifier using this pre-trained LLM and feedback from the humans. And I'm going to train, hopefully, a great verifier so that at the inference time, I'm going to have the generator agent work with the verifier agent to give highly accurate answers to the users. Okay, so that could be an example of a use case to keep in mind as I'm going to talk about theory for this problem. Okay, so I want basically, a use case here would be to try to, so I have a pre-trained generator. It's a good point, but not perfect. And I'm going to train a verifier using the generator and the human on problems of the type that the humans care about, to then, at the inference time, the human just submits queries, and then problem statements and then the generator and the verifier work together to hopefully output a very accurate answer for the user. Okay, so that's the use case to have in mind. Okay, now in this use case, so that's perfect, actually goes back to your question. So if we're going to try to study this problem theoretically, what's the first thing we should be doing? Well, we have less in the room, so less valiant here in the room, so maybe we should try to use a PAC learning or statistical learning formulation, right? So that's a very natural starting point. And so how do we model this problem as a PAC learning problem? So now we're going to assume that we have a distribution over a fixed unknown distribution over instances. And so what our instances here are pairs of problem statements and reasoning traces. And then we're going to assume that in the training phase, the learning algorithm is given an IID sample of such problem instances, which are, again, problem statements, so statements and reasoning traces. So these samples are drawn IID from a fixed unknown distribution. And then they are labeled by an expert. So the expert will tell us for each of these problem statements and reasoning traces whether the reasoning trace is correct, or if not, they will point out to the location of the first mistake. This is what the expert will give us in the training phase. So for example, for the first problem statement and this reasoning trace tau 1, the expert will tell us, yeah, this is a correct reasoning trace for this problem statement. Maybe for the next one, the expert might tell us for problem statement x2 and reasoning trace tau 2, no, there is a mistake, step 3, and so on. Right? So in the training phase, we have such an ID sample of problem statements and reasoning traces labeled by a human expert. And then based on this sample of ID instances, our learning algorithm output a verifier. And as typical in the PAC learning, we want our verifier that has a property that we have high probability over the draw of the training set of typical instances. We want that our verifier will have low error over the distribution, so meaning for most future pairs of problem statements and reasoning traces drawn ID from the distribution, it will correctly state whether the reasoning trace tau is a legal reasoning trace, or otherwise give us the location of the first mistake if it's not. Yeah, that's typical PAC statement. Yeah?
So, do you gain anything from the fact that the expert told you mistake in step 3 rather than no? Like the typical PAC learning is yes or no, and
yeah, so but in machine learning, like there is a whole empirical literature that could be outcome supervision versus process supervision. So what we look at in this framework, outcome supervision, I just tell you, no, it's incorrect, the reasoning trace, and process supervision, I can go and tell you step by step where is the mistake. This is our goal. Okay, so this is, we gain, because when we're going to use it with the generator, you want to use that to do more efficient inference.
So you show better bounds because you get...
So if we are able to point the location of the first mistake, it will help us to get better guarantees than what people do in practice currently with the generators. And I'll come to that, okay? Good, but is this framework clear? So right, this is a natural way to model statistical learning. And I'm not going to go through the details here, but you can prove generalization bounds, the typical sample complexity guarantees that have epsilons and deltas, and the VC dimension. So here the complexity term will gonna look like the VC dimension of the class of Bayes verifiers, the step-by-step verifiers times log L, where L is an upper bound on the length of the reasoning trace. Okay, and the proof, if you're familiar with learning theory bounds, just follows by analyzing the shattering coefficient of the family of functions I really care about. This family of loss functions is my class of Bayes verifiers, and this type of mistake that we are talking about. Point to the location of the first mistake or say correct otherwise. And you go for a shattering coefficient argument and classic VC dimension theory, and you get this bound. Okay, so I'm not going to go into the details of that. But you might ask, is it a useful bound? And it turns out that if you have in mind this, our final goal, it's not necessarily an ideal bound for us. It's not necessarily useful. Why? Because the key point is when I'm going to use a verifier interacting with the generator agent, I might go out of distribution if the generator uses feedback to update its output. So here's a picture. So, this is a generator agent. Again, it's pre-trained, it's frozen. That's why I have a snowflake here. And then I take as input a problem statement X. And then maybe the generator says, oh, here's the reasoning trace. Here is for the problem statement X. Here's the plan for your question about planning a trip to New Rips. And when the verifier agent says, no, I think step 2 is wrong. And now maybe the generator retries and updates the steps through L. Now it goes back to the verifier agent. The verifier agent said, no, step 3 is still wrong. Again, the generator still retries and updates step 3 through L. And then maybe eventually the verifier accepts. But at the time when the verifier accepts, this example is not going to be necessarily from the same distribution as the original set of examples I used to train the verifier on. So there is the output that I get here is not useful at all. I really have no guarantee on it. So the issue is that, again, when the verifier is interactive with the generator agent, we might go out of distribution. So the guarantees from the model that I showed you from our New Rips paper don't necessarily apply. Okay? Now, in our New Rips paper, we had a couple of ways to try to go around that. But I'm not going to tell you about those. You can read in the paper, because they have some drawbacks. And instead, I'm going to tell you about our most recent approach to that problem. Yes?
I have a question with the previous slide. So, as far as I know, in this this inference sample language model, often the assumption is that the verifier is not perfect, and there are many approaches such as backtracking, I don't know, best of, and these.
But we are going to run a verifier. Yeah, in a lot of this literature, they assume that the verifier is given somehow to me magically. Maybe it's a pre-trained LLM. But the key innovation here, actually, we are learning a verifier, and we give provable guarantees for learning verifiers. And we are asking how should you train a verifier so that it has good guarantees for the problem that you really care about. So it's a new perspective. And in fact, I guess theoretically, there is some theory that assumes that the verifier is given to you and it's not perfect. But I think it's better to try to learn it, and we are learning it. And in fact, there is empirical work like OpenAI Let's Think Step by Step by Lightman et al., where they actually showed empirically that if you learn the verifier, it's better. Via process supervision, which is what we do here. Learning a verifier via process supervision can lead to much better outcomes. And in fact, I showed you even the DeepSeek and the Lifty, they use verifier agents, learn verifier agents. Now, the theory papers assume that the verifiers are given to you. I think it's a better approach to learn it, to be good for your problem. So I think this is superior. Yeah?
So in the slide that you show for training the verifier, when you have IAP samples,
Yes.
is that distribution tied to a particular generator, frozen generator? Like the first sample that you sent from the frozen generator to the verifier, is that sample actually coming from the underlying distribution that you mentioned?
Yeah, so let me tell you a better. That was not a great model. So, okay, I want to move to a better model. So let me tell you a better model. Okay, so we had the first paper, and now here is our ongoing work. So, okay, cool. So I just showed a slide to criticize the model. So now let's look at, I think it's a slightly better model. So now what we're going to do, because there is this out of distribution issue, so what we're going to do in the most recent work, we're just taking an online learning approach to training verifiers. So we make no distributional assumptions, at least at the moment when we train the verifier, and instead we're going to bound the number of mistakes. So that's the plan right now. And so here's a picture, a better picture, I think, to think about how we're going to train the verifier. So we have a human expert. They will send problem statements. Now, the pre-trained generator is fixed. I'm just going to assume it's fixed. I'm not going to touch its weight or anything like that. I'm not going to train it. So initially, the human expert is going to send me a problem statement x1. The generator tells us a reasoning trace. Now, I'm also here. I have on this side the algorithm for training the verifier. And now, this algorithm is going to keep updating its hypothesis, right? What the verifier really is. And now, so I have x1 tau1 goes to the algorithm for training to this verifier. I have a current hypothesis. And maybe the current hypothesis for my verifier tells me, no, this reasoning trace tau1 is not correct for the problem statement x1. There is a mistake at step 3. Now, remember, I'm training the verifier. So the human expert is going to tell me whether this is correct, what the current verifier tells me is correct or not. And so going to tell me, no, really, actually, the trace was correct. So I guess the current verifier was wrong. And now I use that feedback to update my current verifier. So to update the algorithm for training the verifier. Now, in the next step, again, I'm going to get a problem statement x2. Now, again, goes through the generator. The generator generates to me a reasoning trace. And again, goes to the algorithm for training the verifier, for my current verifier, right? And this one maybe says, this reasoning trace is still not correct. There is a mistake at step 4. This is the first mistake. So this is the first mistake happens at step 4. And then maybe the human tells me, yeah, that's correct, and so on, and keeps moving. This is how I train the verifier in an online fashion. But yes, the generator is fixed for this process. I'm not touching the generator, yes?
I'm probably missing something, but why does the experts need to get what the verifier is predicting? Can't he just send back the label, there is an error in step 3, and then given what the verifier said, you can know whether the verifier was correct or not by yourself.
Might be cheaper to confirm.
To confirm, yeah, it might be cheaper, exactly. Yeah, it might be cheaper because, yeah. It might be cheaper if you process left to right, exactly. That could be a cost issue, totally. I mean, if you have the true label, like if you, if you have the true label, sure, you can answer this question, whether the verifier was correct or not, but it could be much cheaper, right? Exactly as Jamie said. Cool. All right, so that's the process, and here we make no assumptions about, for now, we make no assumptions about the problem statements coming from a distribution. We're going to assume the generator is fixed, but we are still making this assumption, the generator is fixed. Okay, and what we want to do is want to bound the number of mistakes. And while we're at it, to make things more interesting, because I mentioned AI is used now in very high-stake domains, we also want to differentiate between soundness mistakes and completeness mistakes. So soundness mistakes roughly means accepting correct reasoning, say no too late, and completeness mistakes means rejecting correct reasoning, so say no too early, that's equivalent to that. And you can argue that in some medical diagnosis applications or some other applications, maybe soundness mistakes could be more catastrophic than completeness mistakes. Okay? And so with this in mind, we want to provide refined guarantees that distinguish between these two types of mistakes. And here's an example of a theorem that we prove in this most recent paper. So we prove that for any bound that we have, any bound k on the, any desired bound k on the number of soundness mistakes we're willing to tolerate. There exists an algorithm that makes at most k soundness mistakes, and at most something called the SC Littlestone dimension of the hypothesis class H and K total number of mistakes. Okay, and what is this SC Littlestone dimension of H and K? It's a new notion of dimension that we introduce in this work. And what's interesting is that this is the optimal. This is optimal. Okay, so if you have an upper one on the K of the number of soundness mistakes, there is no algorithm that are going to make fewer mistakes in total than this SC Littlestone dimension of H and K. So basically, you have, I guess, an optimal algorithm for learning this scenario. Okay, and now I'm just going to give, how much time do I have? So I'm going to give you a very quick, this will be very quick for those of you familiar with online learning, if you are very curious what this SC Littlestone dimension is. So I'm going to spend 3 minutes talking about that. So it's basically a tight characterization of online learnability in this scenario. So because we are doing online learning now, instead of shattering points like we do in typical VC theory, when we have distributional learning, instead we're going to shatter trees. And what are these trees right now? What is an SC mistake tree? Will be a rooted binary tree, where the internal nodes will have pairs of problem statements and reasoning traces. And each node we're going to have 2 children, a no edge and a yes edge. And then we're going to say that a tree is shattered by hypothesis class H if for every root, for every path from a root to a leaf, like this bolded path here, there exists a hypothesis in my hypothesis class that agrees with the edge label. So for example, for this bolded path, there exists hypothesis H2 that has the property of H2 of x1 tau 1 is yes, H2 of x2 tau 2 is no, and H2 of x3 tau 3 is no. Okay, and so if for every root to leaf path there exists a hypothesis in my class that agrees with the edge labels, then I'm going to say that the tree is shattered by my hypothesis space H. And then what is the SE little stone dimension of hypothesis class H when I have in most case soundness mistakes? Turns out it's the largest M such that there exists an SE mistake tree shattered by the hypothesis class H such that every root to leaf path with at most k no edges corresponding to soundness mistakes has length at least M. Okay, this is what this S-Hildos dimension of H and K is. And again, what we argue is that for any K, there exists an algorithm that makes at most K soundness mistakes, and that most this S-Hildos dimension of H and K total mistakes. And this is optimal. And the lower bound, if you're familiar with this type of proofs, the lower bound follows immediately from the existence of such a tree. And then the upper bound is, roughly speaking, a greedy one-head look-ahead algorithm. Okay, that uses intelligently the definition of the dimension. Okay, so this is just for those of you that are familiar with online learning. Now, let me go back to the bigger question, how now we can use such a learned verifier to improve a weak reasoner, or sorry, a weak generator. Let's not call it reasoner, because today we've seen reasoning meaning many different things, but let's call it generator. Okay, so let's assume that we're in a situation where we have, so let's call it an alpha weak generator. So it has a property that, maybe say it's alpha weak for a problem statement X. So it has a property that it has probability at least alpha of producing a legal next step that agrees with the target condition on the steps so far being correct. Let's assume that our, 5 minutes, thank you. I think I have enough time, thank you. So let's assume that we have such an alpha weak generator, so for problem statement X, condition on the steps so far being correct has probability at least alpha of producing a legal next step that agrees with our target our target verifier, essentially. Okay, cool. Now, how could we use it? Like, one thing is to do the best of n sampling, like this is what people do in practice. So we're going to generate full traces. So if we have, right, okay, so I guess if we have a good verifier, so if we have a good verifier for the given domain, what we can do, we can generate full traces and verify at the very end. This is called best of n. And so if I have at each step, I have probability alpha of producing a legal next step that agrees with the target, condition on everything so far being correct. In the worst case, I might only have an alpha to the L chance of producing a fully correct reasoning trace. So to really get at least one in our best of n pool to get one correct reasoning trace, I might need exponential number of traces in the worst case, right? So 1 over alpha to the L. But if we do have a trained verifier, instead we can be smarter, and we can use our trained verifier step by step to help the generator build the correct proof sequentially. So, like, you know, if a reasoning step is not correct yet, the verifier, which is now a really good verifier for my domain, can say, no, this is incorrect, retry. And we can only move to the next step once the previous steps are correct. And you can argue that if you do so, like if you build the proof, if you build the reasoning trace sequentially, then you need much fewer alpha, only L over alpha calls to the reasoners, to the generator. Yes?
So is there a hidden assumption that if I get on a prefix that it's correct,
then I can complete it. Yeah, I can complete it. Yeah, but we'll make this assumption. For this result, yes, we make this assumption. And by the way, this is I'm not even telling you full details. This is the high level. But I definitely make this assumption. And also, this is just some sufficient condition in which you can show how you can use a verifier together with a generator. But I think it's an interesting example, because the current practice is best of n can take exponential number of traces, where if you use the verifier intelligently, once you train the verifier for your domain intelligently, you can significantly improve the inference time. Yes?
Just confirming that correctness means like logically entails or something, but you don't necessarily know that that's making progress, right?
It agrees with the human, how the human would think, is that step good given everything so far has been good or not. Just agrees with the human. But doesn't necessarily mean that in an absolute sense you solve some mathematical questions or anything like that. Yeah? But it depends how it agrees with the human. This is my inductive bias here. And by the way, this is just one possible inductive bias. I think I'm going to go now to open questions of this part of the work. As I mentioned already, this is one way to think about what we are doing here is like there has been this work from OpenAI and subsequent work that says you can learn a process reward model via process supervision. This is the kind of the more applied terminology what we are doing, and we have approval guarantees for such a scenario. Except that now at each step we say yes or no. We don't necessarily put a real value number. There are many interesting open questions where you now relax that a little bit. Maybe the output of each step is not just yes, no. Also consider the agnostic case, because right now I'm assuming that there's a perfect verifier in my class. Consider more efficient algorithms. Our algorithms the beauty is that they are optimal. There's nothing better you can do, but they're also not super practical. So can we consider more efficient, more practical gradient-based algorithms? Can we get richer type of feedback, not only about the location of the first mistake, but maybe some other text feedback? Then many exciting open questions in this direction. Other formalization that maybe include the refine agents as opposed to verifier agents, and so on. OK, cool. And I do have 3 more minutes left, right? I promise I'm going to tell you.
1 minute and 2 seconds.
OK, I'll try to do it in 2 minutes. Lenore just told me I'm speaking too fast, so, so I'm trying to not go super fast. OK, good. So I just want to tell you, I guess, because the title was Learning Complex Objects for Modern AI. So I guess one thing we can learn very fast for chain of reasoning. And by the way, it's really interesting. I didn't mention that. So at school, I've actually in this work on learning verifiers, we don't really have just one agent. We have the generator agent, which is pre-trained and fixed, but we also have the verifier agent. So we have 2 agents and the human. So it's in a certain sense 3 agents. So it's already a departure from the PAC model in that sense, for example. OK, so that's interesting. It's more like a cooperative situation, because the verifier is trying to help the reasoners or the generator. So it's not competitive as you normally see in game theory. OK, so that's one thing. Now let me tell you another just at the high level, an area that we've been working on a lot with a lot of my students, including Sid that sits here, which is learning algorithms for solving problems that remain intractable within classic frameworks. OK, and here is the story. So we all know about algorithm design. It's a thing that I guess everybody here knows about. So if we're trying to solve a problem, like maybe an algorithm for solving, I don't know, clustering or partitioning or any type of problem, pricing problems and so on, like what is the classic approach that we think about in theory of computing? So we fix the problem that we want to solve, and then we assume that there is a genius scientist, maybe Santosh. He sits down, he has a stroke of genius, and hand designs an algorithm, right? Analytically comes up with an algorithm, and then if you're a theory of computing person, from a approval guarantee point of view, you're going to worry about worst case instances of the problem. So how does my algorithm do on a one-time, one-shot worst case instance of the problem? So in classic theory of computing, the algorithms are hand designed, and we care about worst case. Now, if you are an economist, you might care about average case, or if you are like in other fields, like operations research, you might do an average case analysis, but still, nonetheless, from a theory point of view, the vast majority of the work on algorithm design thinks about hand-designed algorithms. Now, and of course, for many problems, a lot of these hand-designed algorithms have weak provable guarantees for whatever your performance measure is: solution quality, running time, energy consumption, and so on. Now, because this worst case, just 2 more minutes, because this, you guys asked me too many questions. You asked me too many questions, and that was nice to answer them. OK, 2 minutes, promise. Because this, I guess, worst case, because these hand-designed algorithms have not amazing guarantees necessarily in practice, what are people doing in practice? Well, for almost 20 years now, they said we're going to use machine learning for algorithm design. More recently, they say I'm going to use LLMs for algorithm design. Now, if the keyword is now I'm going to use agents for algorithm design, right? So I'm going to rely on these magic AI systems to produce to me data-driven algorithms, essentially. But now the question is, what guarantees can we provide? Because classic theory in computing, economics, and operations research doesn't provide us any guarantees for these data-driven algorithms. OK, and so this is what we've been doing a lot in the past 10 years in my group with my students. And we've all gone through details because Ishai tells me to not go through details. So I can tell you that we have provable guarantees both in the statistical learning formulation, because you can phrase a data-driven algorithm design as a statistical learning problem. Just my hypothesis class is a class of algorithms now. Or you can phrase it as an online learning problem. Now the question is, what's new there? Well, what's new is that now a lot of it, because they are learning much more complex objects, they are algorithms that have combinatorial modules. Slight tweak in the parameter can lead to totally different outputs. So the loss functions in machine learning terms are very volatile. So it's not even clear you can generalize, right? It's not clear that if you learn an algorithm that does all over past instances, will do any good in future instances. And so this is what we've been developing a lot of cool theory for. a lot of very exciting math for analyzing these data-driven algorithms. And without going through details, all I can tell you is that we have kind of cool analysis, both in statistical learning and online learning formulation, using what we call dual function classes. And and these are just pictures you can keep in mind. So what we argue is that the dual function classes are not too crazy. They are piecewise structured, then you get learnability, what you really care about on these data-driven algorithms. And we had some formalism. Also, Peter Barrett from Berkeley here and Peter Inding and Tal Wagner had some other formalisms, but they are kind of wanting to think about is via dual function classes. Okay, so I'm going to stop here. And by the way, there are still many cool questions. So we mostly ask the question, what guarantees can you get for data-driven algorithms in the classic machine learning sense? But of course, there are many questions about, now people talk about agents for algorithm design. There are a whole new set of theoretical questions you can ask there, because now I might have more feedback than just typical problem instances, which is what we assume currently in our formalisms for data-driven algorithm design. Okay, and I'm going to stop here. So as you can see, there are many exciting theory questions in, I guess, in modern AI. And I'm happy to answer more questions. Yeah.
Maybe I missed this.